Hi, welcome to lesson 9.3. Today we are going to explore similar right triangles. So to get ready for today's lesson, this is what we need to do. So our lesson starts in page 252 of your student journal. On page 253, you need to glue a blank piece of paper to be ready for the lesson. On the next page, we are going to do problem number 1 right here on page 254, problem number 2 here, and on page 255 we're going to do problems 3 and problems 4. So pause the video and get your paper ready for the lesson. Once you're ready, please go back to page 252. Now we're not going to do much on this page, but I do want to explain something about what is a geometric mean. Now we have talked about arithmetic means before in pre-algebra, and that is when you add two numbers together and then you divide them by 2. The geometric mean works almost the same idea, but instead of adding, we're going to be multiplying. And instead of dividing by 2, we're going to be taking a square root. So anytime that we discuss the geometric mean between two numbers, it basically is the square root of their products. So for example, if I wanted to find out the geometric mean between the numbers 3 and 5, all I would have to do is take the square root of their product, okay, and then whatever the square root of 15 in decimal form, then that's what our geometric mean is going to be. Now, why are we doing this? Well, it'll make a little bit more sense after we do the exploration piece. So for this, you're actually going to need 3 different colored highlighters. So make sure you have those handy because they will help a lot in understanding what we're going to be doing. Okay, so what I want you to do is I want you to divide this approximately into half. Okay, divide it into half. Let me scoot back a little bit, let the lighting fix itself. Okay, and what we're going to do here is we're going to draw a right triangle, and we are on purposely making this a right triangle. Okay, just like this. Okay, so the right angle will be right there. And we're going to call this A, we're going to call this B, we're going to call this C. Now, when we drop a perpendicular from the vertex of the right angle, perpendicular to the hypotenuse, we call that an altitude. So we're going to call this vertex right here D. Now, we have created 2 sets of triangles. Triangle 1, triangle 2, and of course we have the original triangle. Okay, hopefully the lighting is working. All right, so let me look at one thing. I'm going to mark this angle right here with only 1 mark, and then this one here with 2 marks. Now, we see that we have 1, 2, 3 triangles. Now, we have already talked about angle-angle similarity in chapter 8. Now, one of the things that I'm going to show you is how is it that this triangle is similar to this triangle, or how they're similar to each other, and how these 2 triangles are similar to the larger triangle. Now, let me say they're similar, not congruent. So what I'm going to do is I'm going to split this triangle into 2 triangles. So this one over here is going to look something like this. And if they don't look exactly the same, that is okay. We're going to call that one A, D, C, and then this one over here, we're going to call that D, B, and C. Now all I did is I split these 2 triangles into 2. All right, now let me remain the markings here. Now we have to think of one thing. How is it that these 2 triangles right here are similar to each other? And how is it that they're similar to the original triangle? So remember that in chapter 8 we learned about angle-angle similarity. And in that, we learned that if 2 triangles have 2 pairs of congruent angles, then they're going to be similar and proportional. So if you look at this triangle right here, not only does it have a right angle, but it also has 1 marking on this one, making it similar to the original because it has a right angle and the 1 marking. So by the third angle theorem, this angle right here will be the same as this one. And for the same reason, this triangle right here has a right angle and this double marked angle, which is the same as the right angle and the double marked angle, making this triangle similar to this triangle. Now, if we use the third angle theorem, that will imply that this angle right here has to be marked with a 1. So this triangle 1 is similar to triangle 2, and this original triangle is similar to pretty much both of these. So they're all similar to each other. Now, I'm going to use a highlighter to identify the corresponding parts, because the angles, we already got them. But it's the corresponding parts that we need to worry about. So let's look at this segment right here. The segment that is made up from this angle and the right angle, which corresponds to this side right here. And on this side, it corresponds to this one right here. So if we're going to be setting up proportionalities, that is what we're going to be comparing to. The next one is the one with the right angle and the double marking. So we have right angle, double marking, and then right angle, double marking. And the last segment, of course, is going to be the hypotenuse, which is made up from the both angles that are marked, which would be this one, and this one, and this one. So what we're going to be doing is we're going to be setting up a couple of ratios and noticing a pattern. So for that, we are going to need the bottom part. I'm going to zoom out a little bit. All right, so what I need you to do is I need you to divide this into 3 equal pieces, where we're going to be comparing, in the first one, we're going to be comparing triangle 1 with triangle 2. On this one, we're going to be comparing triangle 1 with the original triangle, and then triangle 2 with the original triangle as well. Okay. Starting to think the lighting doesn't work very well here. All right, so let's take a look at one thing. Okay, when we're comparing triangle 1 with triangle 2, I'm going to start with comparing the purple. Okay, CD right here is going to be similar to BD over here. Well, hold on, go back. CD, okay, CD is to BD. I was going in the wrong triangle, my bad. So CD is to BD. Let's write that down. CD is to BD. Okay, so this is to this. Okay, as AD is to CD. AD is to CD. Now, when we cross multiply, we are going to get CD quantity squared equal to AD times BD. And then when we solve for CD, that is going to be equal to the square root of AD times BD. Now, if we think about it in terms of the original triangle, CD is the altitude. So we look at this. This is the geometric mean that I was talking about. So CD is a geometric mean between AD and BD. Okay, so we call that the altitude proportionality theorem, I think it's called. So basically, we have CD is the geometric mean between these two. So to summarize it, okay, if you have a right triangle, that does not look like a right triangle. Make a better diagram. Now, I'm going to do this without all the letters because it can get a little confusing. Okay, so say this right here is the altitude. Okay, call that the height. Okay, and I call this one here X and Y. All right, so here the altitude is the geometric mean between the product of the two sides making the hypotenuse. And we're going to get a chance to practice these extensively. All right, so this here is a geometric mean between this one and this one. Now, let's go back and compare the triangle 1 with the original. So let's look at AC. Okay, now we're going to be comparing to this one. So AC, okay, is proportional to AB. Okay, makes sense. AC proportional to AB, and AD, which is this one, is going to be proportional to AC. All right, so once again, we are going to cross multiply, and that's going to give me AC squared equals AD times AB. Okay, so when we solve for this, that's going to be AD times AB. All right, so let's compare that to the original. So we are saying here that AC here is the geometric mean between its adjacent leg and the whole hypotenuse. Okay, so if I was to come up with a diagram with a lot less letters, it would look something like this. Okay, so here, this right here, would be the geometric mean between its adjacent leg and the whole hypotenuse. Now, let's do the same thing with 2. So for 2, we have CB is proportional to AB. Okay, so CB proportional to AB, as BD is proportional to CB. So DB is proportional to CB. So when I cross multiply, I'm going to get CB squared equal to, in this case, it's going to be DB times AB. And once we take the square root of that, we are going to get the following. Okay, CB here is a geometric mean between the adjacent leg, DB, and the whole hypotenuse. So just like the previous one, it's pretty much the same rule, just applied to the other leg. Okay, so we have B, I'm going to call this one here Y, and the hypotenuse still C. Okay, so here B is a geometric mean between B and the whole hypotenuse. So these, ladies and gentlemen, these theorems are the ones that are provided to you. Okay, they're provided to you, but they just look a little bit different. We're going to be practicing using these right here. So if you need a little bit more time to copy all this down, pause the video and then finish taking your notes. All right, on page 254, let's go over these. All right, so the first one is called the right triangle similarity theorem. If the altitude, this one here, is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other, just like you saw in the previous page, where these two triangles were similar to each other and similar to the original. Now, we already discussed a little bit about the geometric mean. The geometric mean of two positive numbers, A and B, is the positive number x that satisfies this condition. That looks familiar, like ratios. So it's basically the product of it being taken, and then after being taken, the square root of that. So multiply them together, take its square root. That's called the geometric mean. And that's where example 2 goes. All right, and then on the next page, we call this one here, these two theorems, the ones that we just discovered. Okay, now something that can get a little confusing because of all the letters. But I like to think about them as, kind of like relationships here. So we have, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments, which we kind of know. These two segments are these two. The length of the altitude right here is a geometric mean between these two segments. So this right here, let me use a highlighter. This right here happens to be the geometric mean between this one and this one. Okay? And then down here at the bottom, we call this one the geometric leg theorem. Basically states that this right here is a geometric mean between its adjacent leg and the whole hypotenuse. So this side right here is the geometric mean between its adjacent leg and its whole hypotenuse. Let me zoom in a little bit if you can see it. Can't see the arrows. Okay. So once again, this is a geometric mean between the adjacent leg and the whole hypotenuse. This is a geometric mean between the adjacent leg and the whole hypotenuse. So when do we use these theorems? Well, whenever we are missing a side of a triangle and we don't know what it is. So which one do you use? Well, if your problem involves an altitude, you probably want to use this one right here. If your problem involves a leg, okay, and a hypotenuse, you're probably using this one. So let's go ahead and jump into our first examples. All right, here's example number 1. It says identify the similar triangles in the diagram. So one of the things that I always like to do is I always like to label this and then separate them. So I'm going to label this one with 1. I'm going to label this one here with 2. Okay, let me zoom in a little bit. Okay, so when I separate these, I'm going to end up with 3 right triangles. Okay, and of course, these are not going to be drawn to scale, and that's fine. I really don't care. So I'm going to make the first one my original, okay, my big one. Okay, so the right angle is at T. I'm going to label this one with 1 arc. That means that that's going to be R. And then the one with a double arc is going to be the remaining one, okay, which in this case happens to be S. Okay, so that's the original. Okay, you want to call this one triangle 1, this one triangle 2, you can do that as well. So that way you don't get confused. All right, so the right angle in triangle 1 happens to be U. Okay, the one with 1 mark happens to be the R, and the remaining angle, well, it's going to end up being this angle right here called T. All right, for the second one, notice that I don't have a marking, but I have a double marking, which happens to be S. The right angle happens to be U, and then the only thing that is needed here will be the T. So the T ends up having 1 marking, and this one here happens to have 2 markings. I know it's a little hard to see in there, but there it is. So these are the similar triangles. So we can state that triangle STR is similar to triangle TUR, similar to triangle SUT. So it takes a little time and practice in order to be able to do something like this. All right, that's example number 1. Let's go ahead and look at the next one. All right, example 2. A roof has a cross-section that is a right triangle. The diagram shows the approximate dimensions of this cross-section. Find the height h of the roof. All right, so we have quite a bit of things that we can actually do here. We could separate all of these and use proportions, or we can use even the rules that we were just using. So I say we separate them first, but I'm going to label them. I'm going to label this one with 1 marking, this one with 2 markings, and then I'm going to label this one with 1 marking, okay, and this one here with 2 markings. And it's kind of hard to see in there. All right, so what I'm going to do is I'm going to do exactly what I just did. Okay, I'm going to recopy it because we're going to use this to find all the distances. So it's going to be y, x, and z. Okay, that part right there is 3.1. All of the hypotenuse is 6.3. I don't care about the units right now. Don't do that to the physicists because then they'll get all mad. All right, so then what I'm going to do is I'm going to draw 3 right triangle looking diagrams. Okay, I'm going to call this one here triangle 1, this one right here triangle 2. Okay, so 1 marking, 2 marking, 1 marking, 2 markings. And let's look at this one right here. This one here, the corresponding angle here is going to be Z. The right angle is going to be W. And the remaining angle here is going to be Y. We'll come back and put all the numbers in just a bit. So for the other one, the right angle is going to happen to be W. The double marked one angle here is going to be X. And then the other one is definitely going to be Y. So let's look at what it is that we do know. we know that xy is 3.1. Okay, so xy, that's 3.1. Okay, we know that zy, this one right here, is 5.5. And that's all pretty much what we know. And we are trying to find what wy is. So we are looking for this one right there. And this one right here, pretty much the same thing. Okay, so I have the option of using, well, I don't have that many options to be honest with you. I have to use these two in order to find out what that, I shouldn't call it x, I should call it h, since that's what we're using. All right, so that is going to be the h. So if I look at this, I can see that this is proportional to this one and this one proportional to this one. All right, so what we're going to do is we are going to set up our proportion, okay, like this. 6.3 is to 5.5. 6.3 is to 5.5. As 3.1 is to h. Okay, whoop, can't see that. So now what we're going to do is we are going to use our calculator and cross multiply. So when we cross multiply, I have 3.1 times 5.5, and that's going to be 17.05 equal to 6.3h. All right, so now what we're going to do is we are going to divide both sides by 6.3, so a lot of decimals here, and h is going to be, according to my calculations, about 2.71. So voila, we found our solution. Now, is this the only way? No, there's multiple ways. I could use the previous theorems that I just learned to figure out what h is. But that would take, I would have to find out what this one is, and then what this one is, and then I can probably do Pythagorean theorem to find out what this one is. Okay, so there's multiple ways. All right. Okay, so let's go ahead and look at the next one. All right, this one's easy. Find the geometric mean of 24 and 48. All right, so x is going to be the geometric mean between 24 and 48. So that one's easy, because all you have to do is 24 times 48, and that is going to be the square root of 1,152. So when I take the square root of that, that is going to be about 33.94. All right, so that's example number 3. Let's look at the next one. All right, now here's where we actually get to apply the theorems that we were discussing. All right, so remember that the altitude is a geometric mean between the two sides that make up the hypotenuse. So x here is going to be the geometric mean between 6 and 3. All right, so that's going to be the square root of 18. So the square root of 18, that's going to be 4.24. That's it. That's all you have to do for that. All right, now for this one, we have to remember that this is the geometric mean between the adjacent leg and the whole hypotenuse. So y is a geometric mean between the adjacent leg 2 and the whole hypotenuse. The biggest mistake people do is that they put a 5 in there. Keep in mind the whole hypotenuse is a 7. So y is the square root of 14, and the square root of 14 happens to be 3.74. So those are the two solutions. Let's take a look at the next one. Example 5. Zoom in a little bit. Okay, to find the cost of installing a rock wall in your school, the gymnasium needs to find the height of the gym wall. You can use a cardboard square to line up the top of and bottom of the gym wall. Your friend measures the vertical distance from the ground to your eye level and the horizontal distance from you to the gym wall. Approximate the height of the wall. All right, so what we have here is 5 feet. We have the distance from the person to the wall, 8.5, and we're looking for this distance in order to find the height of the wall, because the height of the wall is going to be whatever that distance is right there plus 5. So we have to remember here that this is the geometric mean between the two adjacent legs. But you're probably seeing, hey, we do know what that is. Okay, so 8.5 happens to be the geometric mean between the two legs 5 and W. Now hold on. What do you mean? What is that? How can I solve that? Well, very simple. Okay, remember, this is the geometric mean between the adjacent, not the adjacent, but the two legs making up the hypotenuse. So, how do I solve for this? Very simple. How do you get rid of a square root? Easy. You're going to square both sides. Okay, so 8.5 quantity squared gives me 72.25. That gives you 7W. And then what we're going to do is we're going to divide this by 5 to get W equals 14.45. Now that's not the answer. Can't see that? Okay, that's not the answer because we need to go back and plug that in there. Okay, so the height of the wall is going to be 14.45 plus 5, which gives me 19.45. And that is going to be in feet. So that, ladies and gentlemen, is the solution to our problem. All right, thank you for joining us. Until next time.